Okay, let's start. Do you have any questions? All right, so let's return to what we discussed last time. So we were, I think, at 3.4, section 3.4. Let me make sure. Yeah. So the topic there is about computing the expectation by conditioning. Okay. And there's only one formula here, which is that the expectation is the expectation of conditional expectation. All right. And that's the challenge because this is true for any x and y. This formula is true for any x and y. And to be able to use this formula to solve problem, you need to address the following, right? The first thing is to find the appropriate y to condition on, okay? Because as I said, this is true for any random variable y, but if you choose the wrong random variable y, then the formula is true, but you just can't work out what the expression should be, which is actually related to the next step, where you want to be able to decide the conditional distribution of x given y, okay? And we've seen, or you've seen some of these in the previous sections, section 3.2, 3.3, where you were given some formulas, right? Like the discrete case and the continuous case with the conditional density, okay, formula. However, those more or less tend to be, let's say, not useful in the problems that you'll be seeing in the textbook. Well, the reason is, well, I guess the reason is most of the time, what you're dealing with don't really fall under those, the context of those formula. So yes, the formula might be helpful, might be relevant, but probably not really, let's say, applicable. Let's put it that way. Okay. The second one, the only thing we can say here is just kind of read into the context and see what's going on. That's all we can say. Now, one thing that tends to be true by the nature of the problem is somehow, right? So usually what's helpful is consider different cases, right, of y. And that's the reason why you choose the appropriate y to begin with, meaning that when you choose whatever you choose to condition on with different cases, with different values, then you can clearly understand what this is. That's the point, right? If with different cases of y and you don't understand the conditional distribution, then probably what you're choosing to condition on is not the right one. It's not the helpful one, okay? And thirdly, usually x given y, for some cases of y, involves a similar distribution to x, okay? And that's the point to begin with, that basically you don't know what this guy is, right? That's what you're looking for. So what you're doing is by conditioning on another random variable, you hope that what you're looking for will reappear in a different form, okay? And so ultimately what you end up having is an equation with expectation of x, or whatever you're solving for, appearing on both sides, right? Finally, right, what I want to say is you want to understand the order of computation. In the sense that when you take the inner expectation, this one is with respect to y. Okay, sorry, that's nonsense. This is with respect to x. When you take the outer expectation, this is with respect to y. And if you mix this up, or if you don't understand the order of expectations, the computation won't come out correctly. All right. Well, that's the last thing that can be helpful, is that there could be some sort of induction going on. Let's say indirect induction. Basically, among problems of the same type. All right. So all of these are just really helpful hints, okay, for you to solve the problem. The actual problem, well, you just kind of have to get used to the way it's solved. So let's demonstrate these steps, right, with the problems that we looked at last time, which is, right, the kind of family, right, of the problem to look for expectation of x, let's say sub k, where x sub k represents the number of tosses, right, until you get k consecutive heads. Okay, k consecutive heads, where probability of head is p. All right, so basically this right here is what I mean by indirect induction. Well, of course, right, the way you see the problem presented will be something like, well, find the expected, right? Find the expectation of the number of tosses until you see the first head, number of tosses until you see two heads, right? Two consecutive heads until you see three consecutive heads, etc. What you may or may not realize is that these problems are connected. In other words, they're all related in the sense that to solve the next problem, you need the result of the previous problem, right? And so that's what I mean by problem of the same type. They are variation of the same phenomenon, but you want to be able to solve the smaller problem before you can solve the bigger problem. So, for example, right, x1, right, number of tosses until the first head is clearly just a geometric random variable. All right. And well, you can just use the formula, but here, right, we can already start conditioning. And the conditioning is on the result of first trial, right? First toss. And again, this goes back to finding the appropriate y, right? Why is it appropriate for this one? I don't know, because it can solve the problem. Or if you want, because for all cases of y, okay, for all results of first toss, I can decide the conditional distribution, right? For example, if the first toss is a head, I know that the number of tosses is 1. Because, right, on the first toss, I already get a head. But if the first toss is a tail, then I know that I will waste one toss, and then I will repeat, right, the experiment again, independently of the first trial. Okay, so that exactly is what I mean by involves a similar distribution to x. Okay, and consider different cases of y. You see, right, that basically x tilde 1 is not x1, because x1 start counting from first toss. X tilde 1 start counting from the second toss when, right, the first toss is a tail. So they're not the same values, but they have the same distribution, right? They're both geometric, P. And so, right, when you write down the conditional expectation, okay, again, very important, the inner one is with respect to x. What we mean there is, it's gonna work on this guy right here. Right, this one has no expectation because it's already 1. So this will be, right? So let me see how I can write this. Well, you could write something like this. Actually, here, right, it's usually easier to just write this one. But I'll kind of show you. It's usually easier just to write this. Okay. The reason, right, is we kind of skip the middle step where it's like this. The conditional expectation is 1 with probability P, because that's a probability, right, of the first toss being head, and 1 plus expectation of x with probability 1 minus P, because right now we already take the expectation here, and this one happens, right, with probability 1 minus P. Okay, that's sort of the inner expectation step. But for easy problem, people probably just combine them all in one statement. Sorry, I should write x1, right? Okay, and if you bring the x1 on one side and solve for it, you get expectation of x1 is 1 over p. Right? Any question? And then, okay, so where is the induction? Well, you kind of have to work through it a couple of times to see the induction. So, etc. Right? We showed last time that if you work through it for several cases, you start to see that this guy is like 1 over p, 1 over p squared, etc., right? 1 over p to the k. Right? But notice that, you know, if you really do induction proper, then this is just a guess. This is a proposition. You need to prove the induction somehow, right? This is a proposition. All right. How do you prove the induction, or how you show this works overall, or it relates to, right? How would you find this formula in general? Well, you do it by what? Now, for xk in general, then you say that you will condition on xk minus 1, right? Not technically, not well. So okay, it's not really xk minus 1, but it has exactly has that distribution, which is what? The number of tosses, right? Until the first k minus 1, right? Consecutive heads. Okay. So to find the number of tosses, the expectation of the number of tosses until k consecutive heads, you condition a number of tosses until the first k minus 1 consecutive heads. Why? So basically, I claim then this is the appropriate random variable to condition on, right? Which is that random variable y that we're talking about here, right? Why is it appropriate? And notice, right, for xk in general, conditioning on the first toss is not appropriate. Again, the word appropriate here means helpful, okay, to solve the problem. The reason is this, right? Suppose you want to find the number of tosses until you get 3 consecutive heads. Then if the first toss is a head, it's unclear what's going to happen after that. Because, right, if the first toss is a head and the second toss is a tail, well, you're back to, right, the original scenario, because you're looking for 3 consecutive heads, right? But if the first toss is a head and the second toss is a head, then you kind of make some progress, right, toward 3 consecutive heads, but you're not there yet. In other words, it's unclear what's going on, right? There are some problems where you can look 2 steps ahead, all right? Again, just in case, you're wondering, we're already in the context of Markov chain a little bit, but we're not saying that out explicitly, or we're kind of looking at some sort of random processes here, okay? But the focus here is still on the technique of conditioning, but there is that flavor of looking 1 step ahead, 2 steps ahead, etc., right? So this right here, condition on this, is actually in terms of stochastic process, you're conditioning on a random time, on a stopping time, okay? What kind of stopping time? The first time that you get k minus 1 consecutive heads, right? So I'm just pointing out that the nature of the chapter 3 already is in terms of stochastic processes, but the technique that we're working on right now is kind of conditioning. Anyway, right? So if you condition on xk minus 1, on the other hand, the distribution of xk is clear. The reason is because, right? And here actually, right, working through the cases of xk minus 1 is not really an option, because who knows what value of xk minus 1 is. So probably it's something along the line of, right, like kind of 1 step ahead, 2 step ahead, condition on y. So this statement right here should be understood in that sense as well. You want to, by condition on y, look 1 step ahead, 2 steps ahead. How can you do so? Well, the reason is simple, because once you know what the value of y is, then you can say with that value, what's going to happen 1 step ahead, 2 steps ahead. Okay. So here, when you condition a number of tosses until first like that, then clearly, right, it can be that value plus 1, right? Because if you have k minus 1 consecutive heads, then you will get k consecutive heads with probability p. On the other hand, it will be that value and then a reset with probability 1 minus p. Okay, because right, this will be a tail, and then you're back to square one, and then you just repeat the experiment. All right, so that's very similar to, let's say, this, right? So you can say x condition on y is equal to 1 with probability p equals to 1 plus that with probability 1 minus p. Same thing, right? But here we explicitly write down the values of y. Here, right, we can't, but the flavor is the same, right? We are basically looking at 1 step ahead and, right, show what how xk is dependent on xk minus 1. All right. And then expectation of xk, condition xk minus 1, well, there's nothing much here. So the inner expectation falls on, on the x tilde k, right? Because it falls on this. So it will be xk minus 1 plus 1 with probability p, xk minus 1 plus 1 plus expectation of xk with probability 1 minus p. All right. Again, this may seem strange, but keep in mind that here, this guy is a number, right? Is a constant. So therefore, there's no expectation taken with respect to it. The expectation is with, so this guy is random right here, right? When you condition xk minus 1, the randomness is this guy, because you don't know how the experiment, when it's reset, what value it will take, right? And now, when you take the expectation, the outer expectation, then you average out this guy, right? And that's exactly when you need the induction step, right? You need the induction hypothesis, because now the formula you're claiming to be true will be applied to the k minus 1 case, which will be, right, let's say 1 over p, etc., right? 1 over p to the k minus 1, right? Plus 1 times p plus blah blah plus 1 times 1 minus p, right? Plus everything. Like that, okay? And of course, this is just expectation of xk. All right. And then we solve, right? But you see that if we subtract this over here, we're going to get just p times expectation of xk. And then, right, these two expressions added together is just this sum. And it's easily seen, right, that after we divide by p, we get the formula, but with, right, k instead of k minus 1, completing, right, the induction step. All right, so there you go. So this problem or this failure problem, right? Demonstrate, I guess, A, B, C, D for you. And that usually, I mean, again, you may or may not have to go through everything in that order, but a lot of times all of the steps are there, like implicitly. Okay. Any question?
Sorry, how did we get to how do we have 1 over p to the k as the last value?
1 over p to k minus 1 divided by p is 1 p to k, right? Any other question? All right. So let's look at some of the problems that were assigned. So this will be similar, right, to the problem that we discussed, but of a slightly different flavor. So it says what? Suppose that independent trials each of which is equally likely to have any of the m possible outcomes are performed until the same outcome occurs k consecutive times. So, well, here, right, they say let n be the number of times, right, number of trials, of course, until, right, the same outcome occurs k consecutive times. They ask you to show, right, that expectation of n is m to the k minus 1 over m minus 1. All right. So the first thing is, right, do realize how this problem is connected, right, to the previous problem. In what sense? Well, first of all, right, the previous problem we did is the case when the number of outcomes is 2, right? 2 possible outcomes, heads or tails, right? But a crucial difference, though, is that we here solve it for general P, meaning that the outcomes don't have to have, equal, right, likelihood, all right? And so you could say that this formula, when m equals to 2, is the answer to this when p equals to 1/2. And you should check that they are the same formula, right? When m equals to 2 and p equals to 1/2, these are the same answers. But realizing that, you should see that this n notation may or may not be helpful because clearly n here depends on k. And there, right, is also a crucial recognition. Of course, right, n here also depends on m, right? I mean, the number of possible outcomes. However, I'm not so sure if induction on M would be a wise thing to do here. So clearly, right, you would prove this formula by induction on K. All right. And again, this is yet another, right, kind of, you gotta kind of see that that's the case, because it's kind of superficially, right, in induction on K or induction on M are both possible for this problem. Why induction on K and why not induction on M? Well, possibly because of our experience with the previous problem, right? So I don't think, okay, induction on M would work. Meaning what? Meaning that you would want to condition Nk on Nk minus 1, right? The number of times that it takes to have K minus 1 consecutive outcomes, right, of the same type. All right. So let you think about what this should be. Meaning, how would you work out this conditional distribution? Okay. So if you look one step ahead, what should this be? If you look one step ahead, it will be, right, Nk minus 1 plus 1. It will take only one more trial with what kind of probability? 1 over M, right? Because there are M possible outcomes. So with probability 1 over M, the next trial will have the same outcome as that K minus 1 consecutive times. So you will get lucky, right? And only get one more trial, and then you're done. However, right, if that next trial is a failure, and what is a failure here? For example, right, let's say the types are ABCs. Okay, let's say ABCDs, 4 types. So M equals to 4, right? And let's say that you're looking for, let's just say K equals to 3, right? 3 consecutive types, 3 consecutive times, any of these types show up. And so let's say that you have B and B, right? So far. And so far, right, nothing else has repeated twice. So you have something like, I don't know, A, D, C, right? And then let's say D, right? So far nothing has repeated twice. Then the next trial, right? So here, Nk minus 1 is equal to 6, right? So for the next trial, it could be a B, right? With probability 1/4. In which case, you'll get 7, right? It'll take you 7 times, 7 trials to get 3 consecutive times. Or the next time it can be any of the other type. Let's say an A again, right? If you get an A again, then well, you're back to square one, right? Because the pattern is ruined. You just have to repeat, right? You have to repeat the trials. So basically, if the next pattern is not whatever you're looking for, then you will have to look for the pattern again. Does that make sense? Right. So with probability, what kind of probability? M minus 1 over M. Are we clear on this? Okay. So once you set up, right, the calculation like this, then of course, right, so the first thing is to do inner expectation. And the inner condition expectation will hit on, right, NK, which will just give you an expectation. Okay. And then for the outer expectation, right, it will be hitting on the NK minus 1, right? And here is where you use the induction hypothesis, where the number of times it takes to get K minus 1 consecutive times of some type will be this with value K minus 1. So it will be M to the K minus 1 over M minus 1 plus 1, right? Times 1 over M, and then plus M to the K minus 1 plus 1 over M minus 1 plus 1 plus expectation of NK times M minus 1 over M. And right, we use the induction hypothesis to replace NK minus 1 with that value. Any questions so far? All right. And so now, well, what would this be, right? If you, so here, right, this will be subtracting over here, giving you 1 over M, right? And then this plus this, right, is clearly just this value. Okay, but what will this be? Let me see here. So expectation of NK will be 1 second. If I multiply this by m, it will not, right, be m to the k minus 1 over m minus 1, right? So the reason is because if I add this together, I don't think we get that. Okay, so there's an error here, right? The reason is if I solve for this and I multiply by m, I won't get the induction formula. So there's something wrong with how I work out this expression. What would that be? So the error, right? The error would be like this. So basically, right, from the number of steps, okay, from the number of steps it take to get k minus 1 consecutive types, it's true that it'll take one more step, right, to get 3 consecutive types. However, if you fail, then what happens then? What's the number of steps it takes to get to k consecutive types again? In other words, do you waste one more step like this? Do you waste one more step? The answer is no, right? You don't waste one more step in that case, which is, right, again, unlike the previous problem, where either case, right, you waste one more step. Why so? It's important to understand, right? Because these are the reasons why these two problems, they're similar, but they're not the same. The reason is because, right, here you're really looking for just one particular type. In other words, heads, right? K consecutive heads, one particular type. Here, any kind of outcomes, as long as it's consecutive, is okay. Is that okay? Does that make sense? And that's a crucial difference. For example, right here, BBB would work, AAA would work, CCC would work, etc. In other words, if the next outcome is not B, you start counting then. You don't waste one more step. Do we understand? Again, right, the proof of why, that's an error, adding one like this, is that, the induction calculation won't work. And it has to do with the logic, right? The error is that there's no one step wasted when we don't find the same outcome as nk minus 1 in the next step. Any question? All right, let's see if that's true, right? Because again, if that's true, then when we patch this up, we will get, right, the desired answer. So let's see. So this is still 1 over m, right, times E and K, right? But on the left-hand side, what should we get? Well, the calculation then will be, right, similar but we don't have a 1 here, right? So if we were to have a 1 here, then it will be like this. So that 1, right? Let's see how we can compensate for it. Well, the way we can compensate for it is going to be something like minus, right? M minus 1 over M. Is that okay? So let's see if we can put this together. Well, what's the best way? I want to multiply everything by M, right? Let's multiply everything by M here. So if I multiply everything by M, I will get, right? So M to a K minus 1 is M to a K minus M, right? Over M minus 1 plus M minus M minus 1, right? Which really will just be M to a K minus M over M minus 1 minus plus 1, right? Which will be, right, if you add 1 to this, you see that exactly it's going to be M to the K minus 1 over M minus 1, completing the induction step. Any question? All right, so once again, right, I hope that this problem shows you that, right, this kind of conditioning problem, that there's no formula, nothing that would say this must be this must be this. Even for two problems that are very similar, they come out slightly different, right? And you have to understand the language of the problem to know how to handle, right, the conditional distribution. Because, right, just a small error like this, add 1, because, again, we just did the previous problem, so the add 1 somehow, right, wasting 1 step is still lingering there, but that's wrong because it will not give you the right answer. And of course, right, it's wrong, I guess, more precisely because we look for any kind of outcome occurring, right, k consecutive times, rather than one particular outcome. If you look for one particular outcome, then you do waste 1 step if the next outcome is not that type. But here you look for any type, so therefore you just repeat, right? Okay, any question? All right, so let's try the next one. So here, it will have the flavor of flip a coin, right? Until 2 of the most 3 recent flips are heads. All right. Then find the expectation of the number of flips until that happens. This is question number 23. And so it's important again, right, to understand the language here. It's 2 of the most 3 recent flips. What does that mean? Well, that means, right, something like this. Of course, right, with the previous ones being whatever is acceptable. But it's very tricky, right? Because two of the three most recent heads, so it doesn't require consecutive. But if you're not careful, right? For example, this, suppose that the previous one's like this, then, right, notice that here n is not 4 because, right, two of the most three recent heads is already here. You don't have to wait until this one to get two of the most three recent flips heads. So in this example, right, n is actually equal to 2, right? So you don't require consecutive. But because of that, it may be a little more, let's say, elusive, because how do you patch this together? Again, right, it has to do with what do you condition on. Because once you decide the right random variable to condition on, then, right, you're good. So what would that be? For this problem, what is the appropriate random variable to condition on? Well, the answer is you still condition on the number of flips until your first heads. Of course, here, right, probability of head is P, right? So let's understand, right, the situation. Basically, what you're conditioning on is this scenario, that before, right, until Y, everything before that are all tails, or it could be, right, that the first toss is a head, that's fine. But you're guaranteed that before Y, there's no other head besides that head. That's a powerful thing, right, to know. And that's why conditioning on Y is appropriate here. On the other hand, right, you're dealing with two of the most three recent flips. Therefore, right, the nature of the problem here will require you to kind of look 2 steps ahead, okay, instead of 1. So what would that be? If you condition on the number of flips until the first head, how would that work? Well, what it would be? So you get the first head, right? Then if the next toss is a head, then you're fine because then two of the most three recent flips are heads already. So it will be y plus 1 with probability p. Okay. On the other hand, so that's this scenario, right? On the other hand, if the next one is a tail, are you done? Well, the answer is no, because you are allowed for two of the most three recent heads. So that means that you can get a tail and then you can still be okay if right, the next one is a head. So this y plus 2 with probability p1 minus p. Okay. And finally, you're only restarting if the next twos are tails. You should see, right? You should make sure that that's exactly a restart. Why? Because the next two are tails, then even if you get the next one as a head, nothing is going to happen, right? Because not two of the most three recent flips are heads. So if you get two tails, then you truly restart. In other words, it's y plus 2 plus, right, n tilde with probability 1 minus p squared. Okay. And so this is really what we say is two-step ahead, right? Conditioning instead of one step ahead, two steps, right? And the reason is, again, simple, because the problem requires that kind of language. So that's why, right? But notice that still the number of flips until the first head is the right random variable to condition on. Any question? All right. So then let's just write down the whole thing, right? Expectation of n is expectation of n given y. Well, will be what? We know what expectation of y is, right? Y is the number of flips into the first head. Therefore, expectation of y is 1 over p. And then you solve, right, for this, whatever that is. Any question? All right. Let's do one more. So we're gonna flip until the pattern telltale head appears. This is question number 27. Okay. Again, probable head is P, find expectation. All right, so what do we condition on? Well, you're looking for the parent telltale set, right? So here actually is an example where there's several right answers. You could let y be the number of tosses until first tail, right? First tail is just that one. That's fine. But actually, that is a little bit too conservative. Because if you do this, then you will have to do two-step ahead analysis, which is, let's say, tedious. All right, so this is okay, but maybe not the best thing you can do. The reason is, right, you do know, let's call it Y1. You do know the number of flips until the first consecutive tails, two consecutive tails, right? So because we worked this out before, this will be the appropriate random variable to condition on. Because if you know Y2, then it's just one step ahead condition. All right. In other words, right, n given Y2 will be what? Y2 plus 1 with probability P. That means, right, the next one you get is a head. However, if you get a tail, then what happens? If the next one you get a tail, and what happens? Then you just have to wait for a head to appear, right? Notice if you get a tail again, then you do not repeat the pattern. No, you don't. If the next one is a tail, again, this is about, right, being aware of what you're doing. If the next one is a tail, then you already get telltales. Then you just have to wait for a head to appear. So you say here you plus a geometric P. All right. And then this is with probability 1 minus P. Are we clear on this? And so, right, if you do expectation of n given Y2, that will be, right, Y2 plus 1 with probability P, Y2 plus 1 plus 1 over P with probability 1 minus P. And so expectation of n given Y2 will be, right, what's what expectation of Y2? So expectation of Y2 is 1 over P plus 1 over P squared, right? Notice that here, there's no solving for n. There's no solving for this. So in fact, right, this n doesn't repeat. is n doesn't repeat itself, right? Why? Because the problem doesn't really ask for that. And again, if you somehow you try to force the n to repeat, you would get a wrong answer for this problem, at least. Any question? All right. So let's look at the next one. So this is called the Poyas-Ern model, where let's say you have an urn that initially has R red and B blue. So at each stage, meaning there's multiple stage here, a ball is randomly selected and then is returned to the urn with M extra balls, right? Of the same color. Let xk be the number of red balls drawn in the first K selection. A, right? So find expectation of x1, x2, x3. And again, here you see what? You see some sort of induction going on, right? At each stage, you draw the number, right, of red and blue will change, of course. But somehow there's some kind of pattern on how they grow, right? And B is, of course, right, they say ask you to find expectation of xk in general and explain, right, the intuition behind that. And so, right, let's focus on this one first. And again, the question is, what do we condition on? What do we condition on? So for this problem, right, it should be clear that we condition on the color, right, of the first ball selected, right? So what happens? If you select a blue, then what happens? You select a blue, then the number of reds doesn't change, right? So it will stay the same. Now, on the other hand, if you select a red, then what? If you select a red, then the number of reds will be increased by m, right? So therefore, it will be x1 plus m, correct? Sorry, wrong. X1 is the number of reds after the first draw. So this should be just R and R plus M, right? Because initially you have R reds. Okay, X1 is after first K selection. Wait, hold on. Let me try to think. Number of red balls drawn. 1 second. No. Sorry, I'm even reading the wrong language here. Sorry, this is not about number of red balls in the urn after K selection. Is the number of red balls drawn in the first K selection. So the language is actually very very clear on this, meaning that here, right, expectation of x1 is not about conditioning. Why? Because if x1 being the number of red balls, right, we draw on the first selection. Well, how many balls do we draw on the first selection? Sorry, right? This is just reading the wrong language. I was thinking about number of red balls in the urn after K selections. If so, the first selection, right? You draw 1 ball, but of course that's not, but that ball can be red or blue, right? So if you look at x1 itself, what is x1? X1 will be 1, right? You will draw 1 red ball with what kind of probability? R over R plus blue, right? It will be 0 otherwise. That's the number of red ball draw after first selection. So therefore, expectation of x1 is R over R plus B, period. It's x2 that starts to be interesting, right? How do we compute x2, expectation x2? And notice, right, x2 is the number of balls drawn after 2 selections. And, right, it could take values 2, 1, 0, right? It could be 2 reds, 1 red, 1 blue, and no reds. However, right, you see that x2 starts to get complicated. Why? Because depends on, right, how you pick on the first selection. The composition of the urn will change, right? So the urn originally it's red and blue. But after the first selection, it could be either R plus M in blue or R in blue plus M, which, so, right, will influence the probability of you picking the red on the second selection. We understand? And that's where this problem is, let's say, interesting for x2. So for that reason, right, what do we condition on? So x2 is where you start conditioning, right? What do we condition on for x2? Well, the answer is clearly to decide x2, you want to know what was picked on the first trial, right? So therefore, x2 should be conditioned on x1. In particular, right, whether you picked the first red or you did not pick the first red, right? So if you pick the first red, then what happens? If you pick the first red, then x2 itself will become what? 2 with what kind of probability? If you pick the first red, then we're in this situation, right? Then it will be, so you will pick another red with probability R plus M over R plus M plus B. It will be 1 with probability what? So if you pick the first red, the second turn you can still pick a blue, right? Which will make overall number of reds is 1 with probability B over R plus M plus B, right? On the other hand, if the second pick is, if the first pick is a blue, which means you're in this scenario, then you can still pick a red with probability R over R plus M plus B, but you will pick a blue with probability B over R plus M plus B. Is that clear? And so, right? Well, what do we? So how do we write expectation of x2? Well, what would this be? So this actually, right, is about how you work out the inner expectation, outer expectation. How do we work that out? Well, first of all, right, what is this? Remember, right, x1 equals to 1 is fixed. Then you just set expectation with respect to this. So it's 2 times this plus 1 times that, right? So it's 2 times r plus m plus 1 times b, right? On the other hand, expectation of x2, condition x1 equals to 0 is just r over r plus m plus b. Okay. But this, right, happens with what kind of probability? This happens with probability, right? X1 is equal to 1 with probability r over r plus b. And this is with probability b over r plus b. Right? So overall, what is this expectation? So you get this times this plus this times this, right? Well, what would that be? So you got r times b here, you got r times b, right? So you got 2 times r times b, right? But here you got r plus m times r. So let's see that, right? 2 times r plus m times r plus 2rb over r plus m plus b times r plus b, right? So if you factor out 2r, you got so, right, what looks like a scary expression becomes 2r over r plus b. Any questions so far? So, right, let's recap. Expectation of x1 is r over r plus b. Expectation of x2 is 2r over r plus b. Well, what's your guess on expectation of x3 and expectation of xk? And how would you prove it? Well, it's not hard to guess, right? That this is 3r over r plus b. So in general, it looks like it's going to be kr or r plus b. Okay. But in order to do this, right, we need an induction step. How would that work? Well, let's see, right? The obvious thing to condition on is xk minus 1, right? Because notice, right, the whole thing with Poyer's urn is that each stage, the composition of red and blue will change according to what you picked, right? However, notice that something is nice here. That is that the number of increase, right, is m each time you pick. If the number of increase is not always m, but somehow changes, right, along the way, then we're going to be in a much harder problem. In other words, right, so here we do a 1 and 0, right, because clearly on the first pick, you can either pick a red or not pick a red. But here, we do not want to have any kind of explicit value for xk minus 1, because clearly how many values there are for k minus 1? Well, there are k values, right? From 0 to k minus 1. Reds possible for the first k minus 1 turns. So we just want to do an abstract, right, argument, which is what? Well, if you know how many reds have been picked from the previous stage, then clearly you can only be that many reds plus 1, because this time you're going to pick one more, or you stay the same, or sorry, if you pick a blue, yeah, that's it, right? Yeah, you either pick an extra red or you stay the same because you pick a blue. That's it, right? Nothing more. And here, right, how would you decide this? Well, you need to know the composition of the urn, right, after k minus 1 pick to decide, right, the probability of red. But can you? Well, if you pick, right, let's say, right, so xk minus 1 represent the number of reds picked. In the previous n turn, right? Sorry, previous k minus 1 turns. Then what's the composition of the urn right now? Then the urn will have r plus k minus 1 times m reds, right? Because that's how many times you add the red balls into it. How many blues? Well, if you pick, sorry, not k minus 1, sorry, xk minus 1, right? Because that's how many times you pick the reds. How many blues do you have? You have the remaining turns where you add the blues to it. Is that clear? So therefore, right, the probability that you will pick a red will be this ratio, right? Will be this ratio, which is so you add these two together, right? Which is a total number of balls in the urn. Let's see here, right? notice something nice happens here, right? This subtract this is gone, which is very beautiful. And we got k minus 1 times m. Which is kind of right? Doesn't matter how many reds you pick in the previous k minus 1 turns. In total, right? After k minus 1 turns, that's just how many balls you add total, right? Red or blue. So this is the total number of balls. That's regardless, right, of how many reds you picked. And then this is with probability 1 minus that, right? Which is this guy right here. Let's just call this P, right? Just not to repeat this. Okay. Therefore, expectation of xk given xk minus 1 will be what? So notice, yeah. So expectation of xk given xk minus 1 will be this times p plus this times 1 minus p, right? The reason why you want to be careful is because p also involves xk minus 1, which if we're not careful might involve taking expectation of xk minus 1 squared, which we don't know the formula for, right? The only thing we have induction on is the value of expectation of xk minus 1. So we want to be careful that the expression somehow cancel out nicely. In which case, right, we do, the reason is, right, it's very beautiful. This is p and xk minus 1 plus this is just xk minus 1. All right, which by p we mean this expression. So let's write that down now. Because p is not a constant, okay? P here depends on xk minus 1, which is okay when we condition on xk minus 1. But it's not going to be okay when we take the outer expectation. Because then, right, it will be, you have to take expectation of this. Let's write m here, okay? Like that. And so when we take expectation, the outer expectation, then all we're doing is taking expectation of this, right, and this. So we replace that with k minus 1, right, times r over r plus b, which is our induction hypothesis. Hold on. Like this, right? All right, and with some luck, it should shake out to be whatever we want, right? Which is k r over r plus b. Well, is that true? Well, let's see. notice, right? Because this is my this is k minus 1r, right? And our goal is to get to r over r plus k, right? Then this is subtracting r over r plus b. So if our formula is right, if our calculation is right, this better be r over r plus b. Okay, this better be r over r plus b. So we should just work on this expression to see if that works. So this is the common denominator, right? Is r times r plus b plus m k minus 1 times r over r plus b times r plus b plus k minus 1 times m. Okay. So let's see. Yes, right. Luck is on our side. Or we did think. Cancel, leaving you with that. And so that's this expression. And subtracting this exactly is that. All right, any question? All right, so hopefully that will give you enough examples, right, for conditional expectation. Again, the variety of the problem is very rich, right? Different problems require different kind of conditioning. The only thing we can say here is, right, look into the problem itself to decide, right, what's appropriate to be conditioned on. And the computation, you see, relies most on this step. You need to know how to do the conditional distribution. If you can't, then you can't do the calculation down right below. And of course, right, always kind of keep your eye on the price, meaning that what are we trying to get? Because if the answer doesn't match, that means somewhere along the line, your analysis, right, with the conditioning is incorrect. Okay. All right, so let us mention some other materials, some new materials. So two new things we want to talk about today. The first thing is the notion of a compound random variable. Okay. So a compound random variable is made up of the following thing. If you have x1, x2, etc., IID random variable, okay, with mean mu and variance sigma square. And then you have another random variable called n, which is a, let's say, a non-negative well, I want to say integer, but I think natural number, but I don't recall if natural number has zero value included or not. So let's say that integer value, random variable, means it takes value 0, 1, 2, 3, etc. Okay. And by the way, it doesn't have to take all of these values. It can skip in between as long as it's non-negative and integer is fine. Because what are we doing? What we want to do is we want to sum the xi from 1 to n. All right. And if we do that, x is a compound random variable. It's called compound random variable. So what's special about this? Well, what's special about this is, first of all, right, it's a random sum. Well, You've seen random sum before in central limit theorem, let's say. However, in central limit theorem, the upper limit, how many terms you're summing, is a fixed number, like x1 plus x2 plus x3, right? This right here is a fixed number, meaning you know that you're summing 3 terms. With a compound random variable, you can say that you don't know how many terms you're summing, right? Basically, it's different each time, right? Depends on the value of n. All right. A most common choice of n is a Poisson random variable. But it doesn't have to be the only choice. This is the only criterion. So you can have a binomial random variable, okay, or a geometric. But the point is that, right, each time you sum, you don't know how many terms you have because it depends on, not only depends on the values of the x's, but also depends on the value of n. All right. Anyway, well, maybe let's also give an example of what a model of this is. A model of this would be something like, right, especially with Poisson. Poisson, right, describes the arrival, right, of something. So you could have something like, let's say, I don't know, people coming to Macy's, right? Customers arriving, right, at Macy's, according to a Poisson lambda, right, in a day, let's say. So that's n. And then you can have something like each customer spending a random amount, right? And which is true. Customers don't spend the same amount. So let's say each customer, let's say, spends, let's say, a uniform random variable, 0 to, let's say, $1,000, right, at Macy's during the visit, right? And so you see, right, then Macy's total revenue a day, right? Let's say daily revenue, then the amount of money they collect, right? It's going to be the sum of these random variables from 1 to n. Depends on how many customers arrive. That's how much they will collect. I mean, of course, right? The amount. So the amount they spend is random, but also the amount of the customers arriving is random. So that's, let's say, an easiest example, right, of how you would encounter a compound random variable. There are many other, right? You could just make up something using Poisson, right, as your count, right? So n here is called the counting, right, random variable. Well, you can make up a story with a binomial. Who knows? Like if you sum up the binomial, let's say with each success, you get rewarded a random amount, right? You flip a coin n times, but each head, each success, you get rewarded, I don't know, a random amount. So the total money you'll get rewarded will be the sum, right, over this random amount up to the number of successes you get, which is a random number, right? Things like that. Okay. Anyway, so what do we want to do with the compound random variable? Well, we want to compute its expectation and its variance, right? So we'll leave this for later. Let's focus on this for now, right? So expectation of this will be expectation of the sum. So first of all, right, let's ask by linearity, right? This is the formula. Is that correct? Well, the answer is obviously not. The reason being, this is a random variable. So you just have to compare, right? This is a number. Expectation is a number. These are numbers. When you add them up with a random number of times, this is a random variable. A random variable cannot be equal to a number. So that's wrong. Or, to be even more simpler, you cannot pass expectation, right, through a random sum. By random sum, we mean a sum where the upper limit, right, is random. Okay, so that's wrong. So how will we do this? Well, the issue with this is because n is random, right? How do we take care of the randomness? By conditioning. When you condition, then, right, that effectively, whatever you condition on effectively is a number. So you can, is a constant. So you can, right, deal with it. So basically, right, this is a sum like that, right? So first of all, when you fix n like this, then you can pass expectation inside. But so let us kind of say that this is going to be equal to, right, the sum of expectation, right? Notice we're still conditioning. So basically, by fixing n, you can pass the expectation inside, but you're still stuck with condition. All right. And what's the next step? The next step actually is, so that's the assumption here that I forgot to mention, that is routinely assumed that the n here is independent of the x's. Okay. So the upper sum has nothing to do with the value of the summand, right? The number, the amount that each customer spend has no influence on the number of customers arriving, and vice versa. Who knows? I mean, maybe true, maybe false. If you see a lot of people at Macy's, maybe you're more inclined to spend more. Who knows? But it's kind of like reasonable to assume, right, that the amount of people spend at the store has nothing to do with how many people are arriving at that store. Well, it's right. We're saying this is the number of people arriving in a day. It's not the number the customers see when they arrive, right? These are two different things. Anyway, so n, right, being independent of xi, allowing us to drop the expectation. That's very important, right? But you realize that at first you pass it through via conditioning, and then you drop because xi is independent of n. Okay. But then something nice happens because expectation and xi are the same. They are the same numbers. Therefore, you get this to be n times expectation of, let's say, the first random variable, because they're all the same. But now this is constant, so it factors out. And routinely, people assume that, well, we just say, right, these guys have mean mu, so this is mu expectation of that. Any question? So now we want to also, right, compute the variance. And well, you might as well guess it, right? The variance will also involve conditioning on n, which, right, requires to talk about something called the conditional variance formula, which is 3.4.1. All right. Now, it's of the same species as conditional expectation, just more complex. So what is it? A variance of a random variable is going to be expectation of conditional variance plus variance of conditional expectation. Okay. And again, pay attention. It's a rather complex formula. This is exactly why you don't want to just repeat things in math without understanding, because I guess if somehow you try to mimic, right, the double expectation, you might write something like this down, which will be obviously wrong. Well, let's not say obviously, right? It's hard to see that, but it's not going to be the right formula. This is the right formula. Okay. So let's run through the proof of this real quick. So should I do a sum or should I do a, doesn't matter, right? Let's do it with the discrete case. The continuous case is the same, but this is true in general. You don't have to restrict yourself to discrete or continuous case. So how do we do this? Well, the key is again through understanding what the conditioning means. So variance, right, of x given y will be expectation of x squared. You know what? I don't even need, this is proof in general. Minus expectation, right, of x given y squared. Okay, that's conditional variance. And expectation of x given y is a random variable. Therefore, variance of expectation of x given y will be expectation of this guy squared minus the squared of this guy, the squared expectation of this guy. All right. So let's put it together, right? Expectation of conditional variance will be like that, right? And then plus variance of the conditional expectation. But notice something very nice happens. These two guys cancel. And this is the harder thing to handle, because notice this is not a double expectation. Okay? This is expectation of a square of conditional expectation. This guy is really hard to handle, or we just don't know what this is. But luckily they cancel. This is double expectation. And it turns out to be, of course, just expectation of x squared. This is also double expectation because this is expectation outside squared. So double expectation here gives you expectation of x. So that's just expectation of x squared, which of course is variance of x. And that's the proof. All right, any question? All right, so I think it's a good place to stop today. We'll continue, right, with conditional variance next time. All right, I'll see you on Wednesday.